Hi mathematicians, today we're going to talk about continuity. Basically, continuity means that you can draw a function without picking up your pencil. However, that's not a very good mathematical proof. So to prove that a function is continuous, we need to show that the limit exists, i.e. the limit is the same from both the left and the right at that point. The function exists at that point in question, and the limit and the function are equal. So here are some cases. In this case, the function does not exist. We have a hole here, so the function does not exist. In case 2, the limit as x approaches c does not exist because the limit from the left and the limit from the right do not meet, do not approach the same value. This kind of discontinuity we call a jump, because we're going up and we jump down. Another example where the limit does not exist is when we have an asymptote, where the limit's going down or going up to infinity. So asymptotes make a function discontinuous. Finally, we need case 3 to show that the limit and the function are actually the same. Because here, the limit is approaching the same from the left and the right, and the function exists, however, they're not the same. So here we have another hole. In this case, it would be quickly fixed if that point was moved into that hole. We call this a removable discontinuity. The first one is also a case of removable discontinuity because we can put one point in and it becomes continuous right there. So removable means you can fill it in like a hole. And this occurs when you have a denominator with a factor or something that cancels out. Non-removable discontinuities, you can't just fill in with one point. It's a much bigger problem. That typically happens either when you have a piecewise function or you have an asymptote where you have a denominator factor that doesn't cancel, so you get positive or negative infinity. So let's just quickly review our one-sided limits and each part that we will need for this definition. So here's our function h of x. We want to find h of 2. So our function here is equal to 1. And the limit as x approaches 2 from the right is equal to 1. So far, we look like we might have a continuous function if you only look at this right side. Now we look for the limit as x approaches 2 from the left. Well, now we're going up to 4. Right here, we can already see that our function is not continuous because the limit from the left and the limit from the right are not the same. So our limit does not exist, which was our first condition to prove that a function is continuous at a point. Let's look at some more functions. Here we have the function f of x equals 1 over x. So where could this function be discontinuous? It can be discontinuous when our denominator is 0. So that means x must be 0. So let's look at our limit as x approaches 0. Well, when we plug in 0 here, we're going to get 1 over a really small number. So the limit as x approaches 0 of f of x is going to equal something with infinity, positive or negative. So if we're going from the left, a little bit less than 0, we'll have a negative number in our denominator. So we'll get negative infinity. And we go from the right, limit as x approaches 0 from the right of f of x, well, we're going to have a number a little bit bigger than 0, so that will be positive infinity. So we can see the limit from the left and the right are not the same, so we have a discontinuity at x equals 0. What kind of discontinuity is this? When a limit is equal to positive or negative infinity, what do we have? A vertical asymptote at x equals 0. And if we have an asymptote, can we fix that with just one point? No. So this is a non-removable discontinuity. Let's look at another example. Here we have f of x equals x plus 4 over x squared minus 2x minus 24. We have to find where could this function be discontinuous. To do that, we set our denominator equal to 0. X squared minus 2x minus 24 equal to 0. How can we solve this? Well, we can factor. A good hint is oftentimes whatever on the other side in the numerator or denominator is going to be one of your factors, but always test it out. So we have x plus 4 and x minus 6 equals 0. 4 times negative 6 is negative 24. 4 plus negative 6 is negative 2. So now we can set each factor equal to 0. And we get x equals negative 4 and x equals 6. So now we need to determine what type of discontinuities we have here. We know we have two discontinuities. We have to figure out what type. To do that, we're going to take the limit of at each point of discontinuity. So limit as x approaches 4. I'm going to go ahead and write this in our factored form. So if we plug in negative 4, sorry. If we plug in negative 4 here, we're going to get 0 over 0. But we see we can cancel these out, and we can get rid of one of our problems. X approaches negative 4 of 1 over x minus 6. Now if we plug in negative 4, we're going to get 1 over negative 4 minus 6, which is negative 10. So if we get a number here, we still have a discontinuity. However, we know that it's not an asymptote because it's not infinity. So that means we have a hole or a removable discontinuity at, well, here we can even put our point, negative 4, 1 over negative 10. Now let's check our second one. Let's take our limit as x approaches 6. Well, I already saw that it's going to cancel there, so I can go ahead and use that. All the factoring and canceling that I've done. Now, if I plug in 6 here, we're going to get 1 over 0. Well, that's telling me that I'm going to be approaching positive or negative infinity. And if I'm going from the left, plugging in a number less than 6, I think 5, that's going to give me a negative number in our denominator, so that'll be negative infinity. And limit as x approaches 6 from the right Well, that will be a number a little bit bigger than 6, I think 7, so we'll get a positive number in our denominator. So we're going to have positive infinity. So here the limit from the left and the right don't exist, but also because we get infinity, that tells us we have an asymptote. Remember, when a limit as x approaches some number equals infinity or negative infinity, we have an asymptote there. And asymptotes are non-removable discontinuities. Let's look at the next one. Here we have a piecewise function. Now, if we have just a linear graph, that is always going to be continuous. If we have just a quadratic graph, that will also be continuous. All polynomials are continuous. The only point that we have to check here is where we switch from the top to the bottom part. We switch at x equals 0. To prove that it's continuous at x equals 0, we want to find the value of our function, h of 0, and we want to check that it's equal to the limit. Both the limit as x approaches 0 from the left, so if we're going from the left, we're going to use the top part, and that needs to equal the limit from the right. If we're going from the right, that's greater than 0, so we're going to use our bottom function. So let's see if they're all equal. H of 0. So here we have less than or equal to 0, so we're going to use our first one. So 0 plus 1. 0 plus 1 is just 1. So let's see, is that equal to our limit as from the left? Well, again, here we're just going to do 0 plus 1. So far, we're looking good. Let's find the limit from the right now. If we plug in 0 here, we have 0 squared plus 1, which again is 1. So the function h of x is continuous. And we showed all 3 parts of our definition. Let's look at this trig function. G of x equals sine of x. Well, sine of x does not have any denominators in it, and the graph of it looks like a wave. Is this function ever discontinuous? No. Sine is always continuous, as is cosine, but be careful with tangent because that's really a fraction. Let's determine if this function is continuous or not. So we have to use all 3 parts of our definition. The function exists, so we need to find f of some value. Well, we have here a polynomial and another polynomial. So these polynomials are always continuous. So the only point we have to check is 2. So f of 2, does that equal the limit as x approaches 2 from the left of f of x? So from the left, we're going to use this one. X squared minus 4x plus 6. And does that equal the limit from the right? So if we're looking at 2 from the right, we're going to be greater than 2. So we're going to use our bottom part. So let's plug in. If we plug in 2 to our function, we're going to use the top or the bottom? We're going to use the bottom because we have greater than or equal to. So if we have or equal to 2, then we're going to use this part. So we have negative 2 squared plus 4 times 2 plus 2. So that's -4 plus 8 plus 2. That's going to give us 6. Let's look at our limit from the left. Well, if we plug in 2 here, 2 squared minus 4 times 2 plus 6. Well, that will be 4 minus 8 plus 6. That is 2. These are not equal. So we can say f of x is not continuous at x equal 2. And to add to that, what type of discontinuity is it? Well, if the limit from the left and the right are not the same, it will be a jump from 6 to 2 will be non-removable. Just to fill this in, if we plug this in, it's the same as the beginning, 6. So the limit from the left and right are not the same. We have a jump. It's not continuous. Finally, we can have questions that look like this. Find the constant a such that the function is continuous on the entire real number line. Show a complete analysis for your conclusion. So to do that, we need to write all 3 parts of our definition. The function is continuous at that value. Well, we have polynomials again, they're always continuous. We only need to check at 3. So the value of f at 3 must equal the limit as x approaches 3 from the left of f of x must equal the limit as x approaches 3 from the right of f of x. So if we're plugging in here, to find f of 3, we have less than or equal to here. So we can use the first one. A, remember, x is what we're plugging into. A times 3 plus 1. So that will be 3a plus 1. And the limit from the left, that's less than 3. Well, that's going to be the same. A times 3 plus 1. And the limit from the right, we're going to look at greater than 3, so we're going to plug into the second one. A times 3 squared minus 1. Well, we get 9a minus 1. We want to find this value of a that will make it equal. Well, we can ignore this part because it's the same and just solve this equation. So I'm going to subtract 3a on both sides. We get 1 equals 6a minus 1. Add 1. 2 equals 6a. Divide 6. They both have 2, so that's 1 over 3 equals a. So now we can see if we plug in 1 over 3 here, 3 times 1 over 3 plus 1, is that going to be equal to 9 times 1 over 3 minus 1? So 3 times 1 over 3 is like 3 divided by 3. 1 plus 1. 9 divided by 3 is 3 minus 1. We get 2 equals 2. So if a were to be 1 over 3, the limit from the left, the limit from the right, and the value of the function would all be equal. So whenever you have continuity questions, make sure you check all 3 parts.